Hello, welcome. Today we are going to be learning about the Earth as a planet. We are going to be learning about the Earth as a planet. The Earth as a planet. In the solar system, there is the sun, and revolving around the sun is the planets. Revolving around the sun is the planets. One of those planets is the Earth. So the solar system is something like this. We have the sun. Then revolving around the sun is the planets, each of them. So these are the planets. They move around the sun in their own path. So you have the Earth, you have Mars, you have Jupiter, you have Saturn, you have Pluto. All of them are planets. So the Earth is one of the planets that revolve around the sun. This is the sun. You have the planets, 9 of them revolving around the sun. So the Earth is one of them. The Earth is one of the planets revolving around the sun. So the world, the Earth we are living in, is one of the planets that revolve around the sun. So the solar system is made up of the Earth and the other planets revolving around the sun. Until recently, it was believed that the Earth was as flat as a table. So in the olden days, people believed that the Earth was flat, because when you're driving, you drive on a flat plane. So based on that very knowledge, people thought that the Earth was flat. But it has been proved that the Earth is spherical. This is the shape of the Earth. The Earth is actually spherical. It is not flat. It is spherical. It has been proved beyond reasonable doubt that the Earth is spherical in shape. It is slightly flattened at the poles. This is the North Pole, and this is the South Pole. The Earth is a little bit flat here. It's flattened at the poles. It's flattened at the poles to give it a nearly spherical shape. That means that the Earth is not a perfect sphere. It's not a perfect sphere, but it's a sphere that is flattened at the pole to give it a shape known as geode. So this is actually the shape of the Earth, geode. So the shape of Earth is geode. So you see, the Earth is actually one of the planets. There are many of the planets. We have the Mars, we have the Pluto, we have the Saturn, we have the Jupiter. There are plenty planets, 9 of them in the solar system. The solar system, the chief in the solar system is the sun. The sun is the chief in the solar system because it is the object at the middle, whereas the rest of the planets revolve around it. The rest of the planets revolve around it. So the Earth is one of the planets in the solar system. The Earth as a planet in the solar system. So the solar system is made up of the sun in the middle with the planets revolving around it. So having looked at this, we will now look at the Earth in the solar system. We will now look at the Earth in the solar system. The Earth in the solar system. Spacemen have often described the Earth as a beautiful jewel. That's what people that go to the space describe the Earth as. And from the diagram I drew, we have the Earth as a sphere with flattened poles something like this. You have Africa. This is Africa, and this is Nigeria, where we are staying here. Then you have Europe. You have some part of Asia, Middle East. Then you have the South and North America thereabouts. So people that have been traveling to space says that the Earth can be described as a beautiful jewel when seen from the space. So if you're in an aeroplane, or if you fly very high, or using some equipment, you can see the shape of the Earth to be spherical, and you see that the Earth is actually beautiful. The Earth is the only planet which supports existence of plant and animal. For now, the Earth is the only planet. For now, the Earth is the only planet that supports the existence of life. And when we talk about the existence of life, we are talking about the existence of plants and animal. So for now, it has not been proved that there is life in Mars or Neptune or Saturn or Pluto. It is believed now that the Earth is the only planet in the solar system that supports the existence of plants and animals. That's where you can see plants and animals. It takes the Earth about 365 days to complete its orbit. It takes the Earth about 365 days to complete its orbit. What do we mean by this? That it takes the Earth 365 days. Simply means that if this is the sun in the solar system, like I told you, the other planets revolve around the sun. So let's say this is the Earth revolving around this Earth. This is it here, revolving around the sun. The time it takes the Earth to move from here round back to this place is 365 days, and that is 1 year. That is 1 year. It takes the Earth 1 year to revolve round the sun, to start from a particular point and get back to that point again. It takes the Earth 365 days to complete its orbit. The distance between the sun and the Earth is about, the distance here between the sun and the Earth, the distance between the sun and the Earth is the distance between the sun and the Earth. Sorry, I had to off my phone, it's ringing. The distance between the sun and the Earth is 148,800,000 kilometers. That's the distance between the sun and the Earth. This very distance here is 148,800,000 kilometers. It has a natural satellite called the Moon, which revolves eastwards round the Earth once in every 27 days. This our Earth has a satellite. Satellite is a smaller object that revolves around a particular planet. So there is a satellite revolving around this planet. Just like the way the Earth is revolving around the sun, there is also a small satellite here that moves around the Earth. So that satellite is known as the Moon. the small object that revolves around the earth, is known as the moon. And it takes the moon 27 days to move from here, revolve around the earth, and get back to this position. 27 days, which is roughly a month. The distance of the earth from the moon is the distance of this earth from the moon that is revolving around it is 384. This very distance is 384,629 kilometers. 384,629 kilometers. So these are the very important facts you need to know about the Earth as a planet in the solar system. The Earth actually supports the existence of plants and animals. That's why we are living on the Earth. And it takes the Earth about 365 days to move around the sun. This is the sun. It takes the Earth 365 days to move from here and get back to this place, to make a complete revolution around this orbit. 365 days. The distance between the sun and the Earth is 148,800,000. Whereas the distance between the moon and the Earth, which it is revolving around, is 384,692 kilometers. And it takes 27 days for the moon to revolve around the Earth. Very, very important. Yes, welcome back. Today we are going to be learning about the Earth's movement. We are going to be learning about the Earth's movement. What kind of movements do the Earth make? We say that in the solar system we have the sun. Then revolving around the sun are other planets, including the Earth. So this is the Earth that moves around the sun. So this type of movement around the sun is known as revolution. But as the Earth is revolving around the sun, it is also rotating along its axis. It rotates like this. As it's moving like this, it is actually rotating and moving. It's rotating and moving, rotating and moving. If this is the sun, you have the Earth rotating like this as it's moving around it. So it's making two types of motion. Rotation about its axis. This is its axis. It's rotating just like a ball. You just spin a ball, it rotates like this. So it's rotating as it's moving around the sun. As it's moving around the sun, it is auto rotating. So the rotational movement and the revolutional movement around the sun, those are the two movements. So rotation, what kind of motion is rotation? Say that the Earth rotation, the Earth spins. It spins on its axis from west to east. It spins on its axis from west to east. The Earth exists in an imaginary line joining the North Pole and the South Pole through the center. So you have a line, imaginary line. If this is the Earth, you have an imaginary line that joins the North Pole to the what? South Pole. So the Earth now revolves or rotates around this imaginary line. So it takes the Earth 24 hours to make one complete rotation, which is 1 day. So it will take the Earth 24 hours to revolve. Like this very place, let's say this is Africa, it will revolve like this and come back to this very point in 24 hours, which is 1 day. So it takes the Earth 1 day to rotate. You understand? So as the Earth is rotating, it is also moving around the sun. So what are the effects of this rotation? This rotation of the Earth, not the motion around the sun, but the rotation about its axis. What are the effects? Number one, it causes day and night. You find out that, let's say the Earth is here. This part that is facing the sun will be day, but when it rotates, the other side now will become the day, whereas the side that is not facing the sun will be the night. So that is what causes day and night. It also causes difference in local time between places. It causes difference in local time. When we study latitude and longitude, we are going to teach you how local time varies. The rotation of the earth causes the rising and falling of tides. If you go to riverine areas, you're going to see that the rising and falling of tides is actually caused by the movement, rotation of the earth. It also causes the deflection of planetary winds. When winds are coming, due to the rotation, it can cause the deflection of the planetary wind. It also causes sunrise and sunset. You can see that before the day comes very well, which is sunrise, or when it's about to get to the evening, which is sunset, it's all function of the rotation of the earth. The places that are closer to the sun will have full brightness, whereas the places that are not as close as that to the sun will be having either sunset or sunrise at a particular time. So these are the effects of the earth's rotation. Number one, it causes day and night. It causes difference in local time between places. It causes daily rising and falling of tides. It causes deflection of planetary winds, and it causes sunrise and sunset. So I'm going to teach us the other movement of the earth known as revolution. Yes, hello, welcome. Today we are going to be learning about the second type of movement of the earth known as revolution. I told us that there are two types of earth movement. One is the movement that the earth is making round the sun. This is the sun. The earth moves around the sun. It is known as revolution. Whereas if the earth is revolving around its own axis, it is known as rotation, which was the last class we took. So today we are going to look at revolution, which is the movement of the earth round the sun. This is the sun, and this is the earth moving around its revolution. So what is revolution? The earth revolution is the movement of the earth on its orbit. This path that it goes through is known as the orbit. Movement of the earth on its orbit. On its orbit around the sun, and it is done in about 365 days. It takes the earth 365 days to move around the sun and come back to the initial place of takeoff. Every 4th year, instead of the earth taking 365 days to move around the sun, it takes 366 days, and that is called a leap year. That is called a leap year. So on normal years, it takes the earth 365 days to move around the sun, which is 1 year. But after 4 years, it takes the earth 366. Every 4th year, it takes it, not actually after 4 years, but every 4th year, it takes it 366 days to move round the sun, and that 366 days is known as a leap year. The revolving of the earth round the sun is done at an angle of 66.5 degrees to the earth orbital plane. So you see that this revolution is not done in a perpendicular axis with respect to the orbital of the earth. It is actually slightly inclined. So what are the effects of the earth revolution? What kind of things that happen due to the fact that the earth is moving around the sun? What are some of the things that happen due to that? The revolution of the earth causes the seasons. It is because the earth is moving around the sun. That's why you have wet and dry season. You have wet and dry season. Wet and dry season. In Africa, that's what we have. Those are the seasons we have in Africa. It's either it's wet or it's dry season. Like now we are having a little dry season in Nigeria now. So it's either the wet or the dry season. The wet or the dry season is actually caused by the revolution of the earth. In polar regions, such as you can see in Europe or in America, we have seasons like autumn, winter, summer, and spring. Those are the seasons that you have in the polar regions. Also, the revolution of the earth causes summer and winter solstice, as well as autumn and spring equinoxes. So those are the effects of earth revolution. With time, I'm going to explain more how the earth revolution causes dry and wet season and these other seasons in the polar regions, the autumn, winter, summer and spring, and also what winter or summer solstice is and what autumn and spring equinox is. So that is it about revolution. Revolution is one of the movements of the earth, and this is done by the earth. If this is the sun, the earth moving round the sun, that is revolution. I told us that there is also another movement that is done by the earth known as rotation, which is the spinning around its axis. That one causes day and night, deflection of planetary winds, rise and fall of tides, sunrise and sunsets. Whereas this very type of motion, revolution, causes the seasons and summer and winter solstice. Yes, welcome. Today we are going to be learning the shape and the size of the earth. The shape and the size of the earth. What is the shape of this earth that we are living in? Is it flat like the olden people believed, or is it spherical? We know now that the earth is actually about approximately spherical. It has a shape known as geode. That's the shape of the earth, geode. Approximately spherical. The earth is something like this. It's flat at the poles. This is the shape of the earth. It's almost flat here. This is the shape of the earth. We have Africa. We have Middle East, Europe, South and North America. So we have the axis connecting, the S-axis connecting the North Pole to the what? South Pole. So the movement, spinning of the earth about this axis is known as rotation, whereas the movement round the sun is known as revolution. So what do we know about the size of the earth? We know that the earth has the size of 443 million square kilometers. That's the size of the earth. 443 million square kilometers. That's the size of the earth. And the earth is the 5th largest planet in the solar system. You know there are 9 planets in the solar system. The planets are those that are revolving around the sun. There are 9 of them. And the sun is the 5th largest. I mean the earth is the 5th largest of the planets. So there are other dimensions of the earth, like the equatorial circumference. The equatorial circumference simply means the circumference at the equator. This is the equator. This is the equator. So what is the circumference? The distance like this round the equator. This circumference is 40 million. It's 40,085 kilometers. Then we have the equatorial diameter. The distance between from here, from the midpoint of the earth meeting the equator here, is 12,762 kilometers. Now we have what we call the polar circumference. The circumference at the pole, like the North Pole and the South Pole. This distance, this circumference, what is it? It is 39,955 kilometers. And the polar diameter, distance between here meeting the polar circumference is 12,722 kilometers. So they are very, very important that you know. This is the shape of the earth. It has a geode shape, partially spherical, and the earth has the size of 444 billion square kilometers. And the earth is the 5th largest planet in the solar system. The earth is the 5th largest planet in the solar system. It has a It has the size of 443 million square kilometers. Very important. Those are the things you need to know about the shape and the size of the Earth. Yes, welcome. Today we are going to be looking at map reading. Today we are going to be looking at what? Map reading. Map reading is a very important aspect of geography. Whenever maps are presented to you, you understand? Maps are done with signs and symbols. You understand? Your ability to recognize those signs and symbols and say that this sign or this symbol is indicating a school, is indicating a road, is indicating a boundary, is indicating a river, is indicating a valley, is indicating a cliff. You understand? Your ability to identify that this particular symbol or sign is indicating any of these features that I've mentioned is your ability to do what? Do map reading. It's your ability to do what? Map reading. So that's what we're going to be learning. How you're going to be able to tell me, hey sir, this thing is a river. So anytime you see this in the map, it means river, it means cliff, it means this. Is that clear? So now, map reading is the ability to recognize the conventional signs and what? Symbol as used on maps and their descriptions in words of the area mapped with the aid of what? Signs and what? Symbols. Maps are made up of signs and symbols. So whenever you are able to read these signs and symbols and tell us the meaning, then you are able to do what? Map reading. You are able to do what? Map reading. Maps, as we learn in school, can be classified into three. Is that clear? You have the atlas map. You have, some of you have atlas in your house. When I was growing up, my father used to have atlas. You understand? Atlas is the more professional form of map. You understand? It's like a booklet. Some people used to have it in their house. When you open it, you see the map of the world. You open, you see what you see the political map, you see geographical map, you see different types. It's well contained. You understand? Now we also have what called topographical map, showing the topographies. You understand? Then we'll have what we call sketch. One that is sketch for you. Like they want to bring it out in exam, they can make small sketch. You understand? So maps can be classified in either of these, in either of these three. Yes. So let's go on back. Let's march along. So after looking at this, we look at what we call conventional symbols. We look at what? Conventional symbols. I told you that in map you have signs and words. So what are these conventional symbols? They are various what? Signs. Symbols are the various, conventional symbols are the various signs used by the map makers. Used by who? Those people making the maps, is it not? So, represents both the natural and cultural features on the map.
Disorganize the ions. We say for a substance to dissolve water, there must be what? Lattice energy. The energy that requires to break the bonds of that ion. Before we talk about what? Hydration energy. I would say for an epithelial reaction to take place, lattice energy was greater than what? Hydration energy. Why for an exothermic reaction to take place? Lattice energy was water less than water.
Exactly. So conventional symbols are those symbols that you use them every time, you understand? So once you're able to identify what those symbols mean, then you're able to read map. Exactly. These conventional symbols are classified into four. They are classified into four. So we have the four types of conventional symbols that we have in geography. Map exactly. We have what we call number one,
reduction in the level
line symbol. We have what? Line symbol. What kind of things do we like use line symbols for? This like railway, but railway is that another thing. Roads, roads, river, what again? Boundary. Is it not? Give me this example of boundary. You can tell me what these boundaries is showing. This boundary for what? The country was Nigeria. Is it not? This is the boundary. It's using line, isn't it? Whereas this one is showing the river Niger and river what? So we use line symbols for them. Now number two, we have another type of symbol. We call it point symbol. We call it what? Point symbol. You can tell me an example of what you can use point symbol for. Let's say where we have schools, where we have what? Where we have court. Court, you know what court is, right? Magistrate court, all those things. We have post office, right? So we use what we call point symbols for them. Like a point like this, they will write in school. Then number three is what we call pictorial symbol. What we call what? Pictorial symbol. We can give you an example of this. We can use forest. If you want to represent a forest, this is what you draw. So this picture, pictorial. You understand? Another thing we can use pictorial symbol is mining site. What? Mining site. The site where you mine. Exactly. You can also do church. Is it not this is the picture for what? Church, man. Then if it is mosque, something like this, right? But you can also use it for what? Church and what? Mosque. Then lastly, the last group of symbols we have is what we call what? Literal symbols. Is what we call what? Literal symbols. Can you tell me what literal symbols is? Now instead of using something like this to represent school, and you come and write S-C-H. What's the S-C-H? School, huh? Then instead of writing drawing any other thing, call it church or something, you come and write M-R-K-T. What does it mean? Market. So this is literal, you are writing it there. Exactly. So pictorial symbols, can you see pictorial symbols? These are examples of pictorial symbols. This one indicating forest, this one indicating what? Church. Point symbol is when we have something like this. You come here and do point, and you write S-E-S, school, then the first one, line symbol, is like line. So those are the conventional symbols that we use. We are going to verify them very soon. Two types of symbol in one, yes, to make it elaborate. Yes.
And the temperature is 100 degrees Celsius. And the temperature is 100 degrees Celsius. Not be supplied. Energy not be supplied.
Yes, welcome. We're going to be looking at map scale. We're going to be looking at what? Map scale.
After the activation,
anything that you see on paper, you understand, represents something on the
after the
actual ground. Exactly. So if you have a map on paper, then we have a line symbol showing road. If the distance on the map on paper is, let's say, 5 cm, let's say what? 5 centimeters. Then on ground, that distance may be representing 500,000 kilometers. You understand? Because you know that if you're representing a distance, let's say from one place in Kano to another place, because your paper is very small, you can represent it with 5 cm length of line. But on the actual ground, you understand, the actual distance might go up to 10 kilometers. Exactly. So that relationship between the length on paper to the actual length on ground is what we know as what we call map scale. Exactly. So map scale expresses the relationship or proportion between the size of any symbol or indication as used on the maps and that of the actual object it represents. Exactly. So that relationship, that proportion is known as what? Map scale. Example of scale is a scale of 1 centimeter to 1 kilometer. Exactly. A scale of 1 centimeter to 1 kilometer simply means that for every 1 kilometer on ground, it is represented on paper by 1 centimeter. Exactly. So that even if you see the distance to be very small on paper, you know that that is not the actual distance. The actual distance is when you take the scale. You understand? So let's say you have this map. Are you looking at this map? And this map has a scale of 1 cm to 10,000 kilometers. You understand? And I have something here. And the distance here is 5 cm. Exactly. If my distance here is 5 cm, what is the actual distance of between A to B? Distance between A to B is 5 cm. And the scale is saying that 1 cm represents 10,000 kilometers. So what would be the actual distance of A to B on ground? 5,000. No, it's not 5,000. This is 1 cm to 10,000 kilometers. Which is what? 5 times 10,000, which is what? 50,000 kilometers. That's the actual on ground. You understand? But on paper it is what? On ground it is what? Exactly. So now we are going to look at the different types of scale that we have. We are going to look at the what? The different types of mass scale. Types of map what? Scale. Exactly. Types of mass scale. Number one is what we call the what? Linear or graphic what? Scale. Exactly. Number two is what we call the what?
You agree with me that
Statement or verbal scale. Exactly.
You agree with me that
And number three is, and lastly, is what we call the representative fraction.
From acids,
RF,
element that are lower.
or the what we call numerical scale. These are the types of map scale that we have in map reading. Exactly. Number one is what? Linear scale. Linear scale is normally like this.
In brackets, solid and liquids. Solid and liquids. Number three, pressure.
Exactly. Here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly. This is what we call.
The concentration of the reactant is more. When the reacting
This is what we call linear scale.
concentration is what? Number of mole per what? DNP. It means the number of mole of a particular substance.
Here from here to here.
That's what? Solution.
It's known as the what?
For instance, when you are drinking tea, when
Secondary.
you add one spoon of milk,
Whereas from here to here is known as what? Primary scale.
Minus more, the concentration
This is what we call linear scale.
my tea is what? Higher than the concentration of the GNC. You understand? So that's why we speak of concentration. When you add
That's why let me explain it for
when
you.
you get to
I
the
will
add
leave it to
salt
right
water.
now. This is how a linear scale is. So let's say you have a graph
The mass divided by
given to you.
the atomic mass. And it's
Then we have here is
you
Okene.
get to the same point, the concentration is so high.
Then from
that
Okene
salt
to
precipitates out of water.
Ampa.
You add one spoon of salt to water and you stir it.
Now, they want you to measure this end using this scale. You use a paper. You place from here to Ampa. You know the distance. Exactly. You come and place that distance here. And this is measured in what? This one is measured in kilometers. Exactly. So let's say you measure this and the distance is from here to here. What will be the measure from here to here? What will be the distance? 3 kilometers. You understand? But you know that the actual paper on a plain sheet cannot go up to kilometer. You know what a 1 kilometer is? You are traveling on road, you start from here, get to that far before 1 kilometer. You understand? So you read it off with a paper or a divider. You understand? Then you come and place it on the scale. Anything it gives you on the scale, to the nearest what? Kilometer, that's the actual distance. Then what you have what you call what? Statement or verbal step. When we say
surface area of the reactants.
1 centimeter is what?
Surface area of the reactants.
1 centimeter is what?
Area of the reactants.
Equal to how many? 1 what? Kilometer, is it? So this is a verbal scale. It's telling you that anywhere you see 1 centimeter in a paper, that it actually means that on land it's actually 1 kilometer. Exactly. This is what? Verbal word or statement. It's written in form of statement. What if you have 1 is to 50,000? This is what we call what? Representative word, fraction. Or you call it what? Numerical scale. It's a form of numbers, is it not? It means that anywhere you have 1 centimeter, that it actually means what? 50,000 centimeter on ground. Exactly. Or 1 centimeter actually means 50,000 kilometers on what? Ground. Exactly. So the first one is the distance on paper, and the second one is what? Actual distance. Exactly. Distance on paper. Then what? Actual distance. Distance on paper, what you use your divider to measure. Then you place it on this one and read off the word. Actual word. Distance. Do you understand? Do you understand? So we'll stop there for now. Next class.
But if you want to take, if you want to use cube figure, what will happen? Social relevance.
Yes, welcome. Today we're going to be looking at map copying. We're going to be looking at what? Map copying. How do you copy a map? If a map is given to you and you're expected to receive it, you understand? Somebody gives you a map of Africa. Say, please copy this map into a piece of paper so that I can use the one I have to do another. You understand? You have only 1 copy of a map. Let's say there is no photocopy machine for you to photocopy. You need to draw it by yourself. You understand? They call it map copy. Your ability to reproduce a map as it is in the original paper that was given to you. Exactly. So say that map copying is the ability to reproduce a given map extract as it is initially. Exactly. Whenever you can reproduce a given map as it is initially, then you can do what we call map copying. Exactly. Whenever you can reproduce a map as it is initially, then you can do map copying. How can you copy a map? You normally copy a map using what we call grid lines. Using what we call what? Grid lines. Grid lines are something like this. In a paper, you have horizontal and vertical lines. Exactly. So whenever you have horizontal lines intersecting vertical lines, you produce what? Grids. You produce what? Grids. All these things are known as what? Grids. Exactly. And these are the grid lines. And these grid lines can be nothings or pistons. They can be what? Nothings. The vertical ones are known as what? Nothing. Whereas the horizontal ones are known as what? Pistons. Why is it called nothings? This is going towards the north. Pistons because it is going towards the east. Exactly. So those are the Those are the green lines. So let me explain what we mean by copying a line. Copying a map. So let's say you are given a map extract, like I told you before, with the shape this. You say that this is the shape of Abuja, isn't it? So you are told to reproduce this thing. How do you do it? Very simple. You understand? This one that is given to you, use a pencil. You know pencil, you can clean it up. Draw a what? Green line. So let's say you are using only 5. 1, 2, 3, 4, 5. Is it not? Draw another one. 1, 2, 3. Just make sure you note the amount you draw. You understand? Now get the paper where you want to copy this to. Let's say this is the paper, huh? This is not the paper. The paper might even be bigger than this one. But don't worry about whether it's big. You understand? Now you divided this one into how many? 1, 2, 3, 4. Yes? Make sure you divide this one also into 4. Huh? So to divide it into 4. So you can now understand that is it not 4? But you might need to use a divider so that you measure it accurately. You understand? Make sure you divide it into 4. You understand? You measure the length of this one and divide by 4. If the length of this is 20, say from here to here is what? 20. If you divide it by 4, it will give us what? 5. Is it not? So it means that the length of each one is what? 5 cm. Is it not? Now, if you are copying to this one and the length from here to here is what? 4. You understand? Also divide by what? 4. Huh? And if you divide by 4, it will give us what? 10. Isn't it? So from here to here should be what? 10. Isn't it? So do the same thing to the horizontal.
The first one we say
you understand? So when you finish, how do you now copy? Just look. The edge of this one, is it the first or second or third or grid? Which grid? It's in this grid, right? So I can easily come and do something like this, which will represent this one, right? Then this one goes from here to the last grid, right? So I can do something like this. The last grid, right? Then it goes like this, isn't it? Is it not? Then it goes to the last grid here. Then it comes, it intersects with this one. Is it not? And comes like this one. So what happens? It goes down, huh? And goes up here and joins this one. Is it not? Have I not copied this? With the end of what? Three lines. That's what you use.
So the next one is waggle dance.
Can you see that map copy?
Waggle dance.
Can you do it? You can do it very simple. Make sure you know the distance. You understand? Then divide it by the number of grids that you want to use. Yes? Divide also this one by the number of grids. The same number of grids. If you are using 4 here, you must use 4 grids here. If you are using 5, you are using 5. You understand? Then make sure you look at this and do the position. Then we don't want to go what map copy. Exactly. Exactly. Thank you.
These are the waggle dance looks like. And the round dance.
Yes, welcome. Today we are going to be looking at map reduction and what? Enlargement. As a geography student, you should be able to either enlarge or reduce map. Is that clear? When you're given a very big map, now they want you to draw it in smaller form. That is reduction, is it not? Is it not reduction? Or you're given a very small map and they want you to draw it to be bigger so that people can see it very well. That is what? Enlargement. Is it not? Enlargement when you enlarge. Reduction when you small. When you make smaller, isn't it? But how do you know that you need to enlarge or reduce a scale?
Well, yeah, interest rate is what?
That is what we are going to learn today. Now, students should be able to prepare a simple map in different what? Scale. You understand? It's the scale that determines whether the map is big or small, isn't it? So as a student of geography, you should be able to move from one small scale to big scale, or from one big scale to a smaller scale. This can be done with the knowledge of what map enlargement and what reduction, which is what we are going to teach you now. But very importantly, you need to note that if the denominator of the scale of the map to be drawn, are you looking?
Yes.
The denominator, this thing is a representative scale, is it not? 1 is to what? 150. What is the denominator? Is it 1 or 150? 150. The numerator is 1, the denominator is what? 150. Now it's telling us that if the denominator of the scale of the map to be drawn, this is the one to be drawn, is what? Bigger than the denominator of the one that is given. This is the one that is given, 50. But the one they want you to draw now is what? 150, is it not? If that is the case, then the students should do map reduction. But if the denominator of the given is bigger than that of the one to be drawn, you should do what? Enlargement. Exactly. So whenever you're giving map reduction or enlargement, they must give you the scale of the given map and the scale of the one they want you to draw. Exactly.
Yes, sir.
So looking at these two things now, are you supposed to do enlargement or reduction?
No?
So you understand? If you look at it when you draw it, you see that you will see actually what you want to do. But when you're looking at the scale, it's confusing. You understand? If you're moving from here to here, you do reduction, not enlargement.
Okay.
Exactly. And that is what is written in this statement. If the denominator of the scale of the map to be drawn is bigger than the one given, you should do what? Reduction. And that is the case. So by what number do you reduce? How do you know the number you reduce? Just divide the bigger one by the smaller one. 150 divided by 50. How many? 3. So you reduce the map by 3 times. Exactly. So if they give you a map with this scale and say reduce it to this one, what it simply means is that you should just divide the size of that map by what? 3 times. So let's say they gave you this map and say you should reduce it. So it should be something like this, is it not?
Yes.
So you see that this map, no matter that this is 50,000, is bigger than the one that is what? 150,000. That's what we say when we are learning type of map scale. We say that maps for small area of land are known as large scale, you know. Then those for large area of land are known as small scale. Exactly. So these two, land with these two now, which one is bigger? This one is bigger. This one is smaller. So that's why you have to do what? Reduce. And how do you reduce? You put the bigger one over the smaller one. Any factor that you have, that's what you use there. Exactly. So now, with that we are going to stop. So when we start actual reduction and enlargement, you understand this.
Which one comes first? Go back to the diagram.
Yeah. Yes, Marianne. Today we are going to be looking at types of scales of map. You understand? Whenever you have a map scale, it's either you are having a large scale, small scale, or medium scale. Large scale, small scale, or what? Medium scale. Those are the 3 types of scales that we have: large scale, medium scale, or small scale. So how do you identify that you have a large scale or that you have a medium scale? How? A large scale is a scale for maps of small area. Large scale or small one. What do we mean by small area? Physically, it's a small area. Like the area of this Tclassified, you understand? The area of your school, your secondary school, you know the area is small. You can easily walk around the area, you understand? So any scale that is telling you about scale of small area of land, call it what? Large scale. Call it what? Large scale. Example is what? Small compound, like in your house, you understand? Your school premises, a small city. They are always having large scale. Because why you call it large scale? If you do 1 over 4,000, and when you do 1 over 10 million, which one is bigger? 1 over 4,000 is bigger. You understand? But you can see that it's in the scale of a very small area. Every 1 centimeter represents maybe 4,000 kilometers, 4,000 meters. You understand? But this one, every 1 centimeter represents 10 million. You understand? So this one is the scale for a large area of land, several kilometers. But we call it what? Small scale. You understand? So when the scale is talking about small area of land, we call it large scale. But when it is talking about large or several kilometers, we call it what? Small scale. Exactly. But if the scale is in between this and this, if it's not too small and it's not too large, we call it what? Medium scale. So now, how do you identify a large scale map and a small scale map? Just look at it. You see that the difference between these two is very large, like here. We call it what? Small scale. If it is not so large, we call it what? Large scale. Exactly. This one is 1 is 4,000. It's small. So 1 is 10 million. It's very large. But example of large scale is when you're talking about the continent of America, the whole continent, or continent of Africa. You know, it's a very large expanse of sand. Together. So when the scale is talking about small area, we call it large scale map. When the scale is talking about large area, we call it what? Small scale map. That's it about. So we look at the next topic. Look at the next one. Next topic. And we call it measurement of distance on map extract. Measurement of distances on map when you want to measure a distance on a map, how do you measure it? Let's say you are given this map. Understand? Then they draw. You know the city that has this shape like this? This is Abuja. So this the shape of the map of Abuja. And now you have here, let's say here is Karo. You know where Karo is? Then here is what? Gwagwalada. I'm assuming that's not the real history. You understand? Then you have a road connecting Karo to Gwagwalada, and they ask you to measure this. How do you measure it? You understand? And you know you have something like this. If you have something like this, what do we call it? Linear scale, man. But you know there are many scales, man. They might give you a linear scale as well. But if they say measure this length, even before you start applying it to the linear scale, how can you measure the length on the map? Measurement of lines along straight line. Along what? Straight line. So it might be straight or it might be like this, back. Isn't it? So it could either be what? Straight or what? Curve, back. Or you call it also what? Winding distance. So how do you measure? Use rope, back. For straight, what do you use? Straight is very simple. To measure a straight distance like this, you can simply use what? You can use one ruler, huh? That one is very simple. But to measure a winding distance, what are the ways you can use in doing it? Number one, you can use a thread. Number one, you can use what? Thread. To measure a straight line like this one, you can use a ruler, very simple. But to measure a winding distance, like something that moves like this and goes to this place. Let's say this place is you understand? To measure distance like this, you can either use a thread. You know what a thread is, isn't it? Or you can use what? You can use a pair of divider, huh?
That's only
You can use what?
disrupt your next
Pair of
disrupt your net
dividers.
So what happens is that
Pair of dividers. You know what it is inside the master.
How can you use pair of divider for your winding?
Like in the start, I will show you now.
you just drop it.
Then lastly, you can use a
So they have
straight edge piece of paper. You can use what?
Straight edge
so they
piece
have
of
very
paper.
sharp, they have
Piece
brightest
of
color.
Paper.
They want it to show just
So these are the three ways you can use in measuring
on it.
distances that is winding, that is not straight. Exactly. It's either you use a thread, use a pair of dividers, or use a piece of what? Paper.
They're very dangerous. So that's the type of warning collaboration. They warn away, they warn away.
So you asked me a question, how can you use a pair of dividers to measure a winding distance? Isn't it?
Adaptation.
A pair of dividers is something that looks like this, but
They have adaptation. Yes, right.
do you know that in any winding, this is a winding distance, but this is a what? But now you use your pair of divider. You can divide this thing. This winding distance can be divided into straight lines. This is the first straight line, but isn't it? From here to here is also what? A straight line. Isn't it? From here to here is also what? Straight line. From here to here is also what? Straight line. Here to here, is it not a straight line? Here to here, is it not a straight line? Here to here, is it not a straight line? Here to here, is it not a straight line?
Number one,
Straight line.
obtaining food.
Straight line.
Obtaining food.
Straight line. Straight
Obtaining
line.
food.
Can you see? You can divide a winding distance into what? Straight lines, isn't it?
But
You place your divider on this one, quicken, and you get it to be what? 5 cm.
Escape and
Quicken, you get it to be what? 3 cm.
but three.
Quicken, you get it to be another what? Quicken, another 2. Quicken, then later what do? You add it up, then it's still the same distance, is it not? So that's why you can use either a tray, pair of dividers, or piece of what? Papers. But this piece of paper has to be straight, not a piece of paper with no straight. So that you can easily, once you pick the distance, you can put it on a ruler and know the actual distance. That
Now, the next one is what?
so these are the ways you can measure distances on map what? Extract. Like I told you, this is an example of a map extract. Map of Abuja, is it not? So you can either, the line you're measuring, the distance can either be straight or what? Winding. For straight lines, it's easier to use one ruler. But for winding distances, you use thread, pair of dividers, or piece of what? Straight edge paper. Drainage patterns. Drainage pattern can be defined as the shape taken by a river and its tributaries. So that shape that is taken by a river and its tributaries is known as drainage pattern. It is an important factor in landform development. Hence, it is usually shown on topographic maps as drainage features. On the other hand, drainage pattern is the whole process of carrying groundwater away from the moment it falls on the earth's surface as rainwater to the time that some of it reaches the sea. Drainage can be on the surface, and this happens when the rivers actually flow on the surface and empty the water into a much bigger water body. When drainage is formed under the ground, it is called underground water. So you need to understand that whenever you hear drainage, it simply means the shape taken. Whenever you hear drainage pattern, it simply means the shape taken by river and its tributaries, that's its branches. And that when drainage is formed under the ground, it is called underground drainage. So take note of this. However, when describing the drainage system of any surface, it is very necessary for the map reader to 1. Note and mention the major river and its direction of flow. Example, in River Yinka flows from northwest to southeast of the mapped region. Number 2, the reader should also remember to establish whether the river has tributaries or not. E.g., the river has too many tributaries. You should also remember to mention the nature of the river valley. E.g., the river's valley may be steep side, flat bottoms, or the river meanders. Also, you should remember to mention the pressure of swamps. Oxbow Lake, the contour lines will guide the reader to know at which point does the river widen out, e.g. between 600 meter and 800 meter, etc. Should also remember to mention the drainage pattern identified in different parts of the map. So how does he identify a drainage pattern? That's the next thing we are going to look at. Types of drainage pattern. It is very important for the user to properly understand and identify the various patterns that occur along the course of a river. There are about 30 different types of drainage patterns. Among these are anastomosing, subdendritic, contorted, dichotomic, yazo, lacunate, phantom, kettle hole, etc. The most common types of drainage patterns are dendritic, radial, trellised, centripetal, annular, and rectangular drainage patterns. Now, first of all, let's look at the dendritic pattern. This pattern is usually found in areas of relatively homogeneous rock, where there is the same degree of resistance to corrosion. The incipient stream normally join the parent river called consequent at an oblique angle. So whenever you hear the word oblique angle, whenever you hear that the tributaries are joining the main river at oblique angle, know that we are talking about dendritic drainage pattern. The resulting drainage pattern assumes a tree, or whenever you hear the word tree form and its branches. Therefore, its name is from the Greek word dendron, which means a tree. Example is the Orange River in South Africa. It has this dendritic pattern of drainage. Now let's look at trellised pattern. This drainage pattern is found or developed in areas where there is alternate band of hard and soft rocks. The most noticeable feature of this drainage pattern is that the secondary tributaries flow parallel to the main stream. These tributaries follow the soft rock and join the main stream at right angle. They are ideal for the process of river piracy. So you see that whenever you hear the word right angle, the tributaries joining the main river at right angle, then you are talking about the trellised pattern. Or whenever you hear alternate band of soft and hard rocks. Now let's look at radial pattern. Radial drainage pattern tends to develop in areas of large conical hill. So whenever you hear the word large conical hill, or area with volcanic cones, then we are talking about radial pattern. The drainage radiates from the conical point. The streams radiate outwards, forming a pattern like the spoke of a wheel. Now let's look at annular pattern. Annular pattern of drainage is made up of ring-like pattern, which is usually formed as a result of interruption of the former stream channels by the formation of crater occupied by the lake. The ring-like pattern so formed is called annular pattern. So whenever there is a lake forcing this to be formed, we call it annular pattern. So those are the major types of drainage patterns. We have the dendritic pattern, we have the trialized pattern, we have the radial pattern, and we have the annular. Dendritic, whenever there is evenly distributed form of rock and joining the mainstream at oblique angle. Trialized, when there is alternate band of hard and soft rock joining the mainstream at right angle. Radial, when there is volcanic cones or large hill in the path of the river. And annular, when there is a formation of crater occupied by a lake. Please, if you like this video, hit the subscribe button. If you have any questions and concerns, drop it on the comment section. If you want to contribute to our growth or collaborate with us in any way, check our phone number and our contacts in the description section of this video. Thank you for all your subscriptions and support. Always share our videos so that your friends can see them and learn from them. Thank you and God bless you. Yes, now the denominator of this is a map enlargement exercise. And you are given that a map is drawn to a scale of 1:50,000, showing an area in Togo. Now you're expected to draw this same map with the scale of what? 1:25,000. What are you expected to do? Is it reduction or enlargement?
Enlargement.
Why is it enlargement?
Because the denominator
Of the given is bigger than the denominator of the what? Expected. Is that clear?
Yes, sir.
So whenever you're given the scale of a map, check the denominator of the given. Denominator, like I told you, 1 is the numerator, 50,000 is the what? Denominator. Anything here, when you say 1:50,000, it's the same thing as saying 1/50,000. You understand? So if the denominator of the given is bigger than the denominator of the what? Expected, then you know you need what? Map what? Enlargement. But if the denominator of the given is less than the denominator of the expected, then you know that you need what? Map reduction. Is that clear?
Yes, sir.
So now, how do we find out what to reduce with? If you want to know the factor of the enlargement, just take the bigger one. Which one is the bigger one?
50,000.
50,000 divided by the smaller one, which is what? 25,000. What will be the answer? 2, huh?
Yes.
So you are enlarging by 2. So now let's say that they say that a map is drawn to a scale of it's showing a place in Togo, isn't it? So let's say that this is the map. Is it not?
Yes.
Showing the place in Togo, huh? So let's say that this is the road, bah? This is a road in Togo. And they say you should establish the settlement known as what? Yan. Huh? Then what again? Okay, this is the river, bah?
Yes.
Then this is the road. Let's say this is the road. So now, come and enlarge this map for me. This is to a scale of 1 is to 50,000. Now draw this map to a scale of 1 is to 25,000. By the way, this scale 1 is to 50,000 and 1 is to 25,000. Which one is bigger? The smaller one is always, the one that looks smaller is always bigger.
Yes, sir.
So let's have you enlarge that scale. So first of all, you have to know the factor you're working with.
Yes, sir.
So given that from here to here is 10, and from here to here is 12. So start work. You're dividing into how many? 5, Good. So you can actually have your grid into how many you want, or make sure they are equal. So how do you know the space of this grid? 10 by 5, which is 2. So you'll be measuring to 2 centimeters. 2 each. Good. So this one, how many are you dividing into? 6. So how do you know the number of the distance? 6 divided by 2. No, 6 divided by 2 now. Okay, 6 divided by 6. 12 divided by 6, which is also 2 cm. So you give them 2 cm. Yes. You don't pass. Good. Because you are not using ruler. But if you are using ruler, they have to be equal. Now, produce the new one. So how do you know how to draw that one?
Multiply by 2.
Multiplying by 2,
Yes,
so meaning that the total distance is how much? For here is how many? 4, which is a total of 20, 20. Then for here is what? 12 times 2, 24. So divide equally the same number of grid lines. 6. One, 2, 3, 4, 5 and 6. So it's complete. Then the other one.
5.
Yes. So you've done the scaling very well. So the next thing is what? Copying. Or copy. Second one. Ending. Go off. Like he wants to hit this man. Then it goes up. Then it enters inside here. Then it comes out. Then it goes down and drops. And it's good. Locate here. Okay, want to do that one first. Count 1, 2 there, and the next one go at the middle. Up small. Yes. Yes. Go down into the other line. Into the other line, go down. Yes, into the other one. Into the other, yes. Into the other one. No, enter the other one first. No, you go enter the other one. You go enter there. Did you open it? No, enter. Good. Out. Thank you. Every sketch. Nice one. So locate here. Nice one.
Bloody set.
So that's how you do it. That is map enlargement. You've enlarged from here to here. It's very simple. It's very simple. And with that, like I told us, we can always locate, we can always know whether we are doing reduction or what? Enlargement. Once you look at the two scale, the given, this is always the given scale, the one they gave you, then the one they are expecting you to produce, is it not? So if you look at it, once the denominator here is bigger than The one here, you know it's enlargement. But if this one is smaller than this one, you know it's what? Reduction. So how do you know the factor you enlarge with or the factor you reduce with? Just take the one that is bigger or divide it by the one that is what? Smaller. Anything you get is the factor. So you can use that factor to either do what? Reduce or what? Enlarge. Just multiply by that factor. Exactly. Exactly. So once you get this, if you are given this map on a paper and maybe they did not tell you this length, what do? You use your ruler and just measure it, is it not? So that if you are enlarging by 2, you just multiply by 2 and draw. But if you are reducing by 2, you divide by 2 and do what? Draw for the next scale, is it not? So they either give you this or sometimes they will also give you some reading on your paper. So anything you have there, measure it and divide or multiply by to either enlarge or what? Reduce. Is that clear?
Yes, sir.
Hello, welcome. Today we are going to be looking at illustration of map reduction. Illustration of what? Map reduction. There are 2 ways that you can use in identifying a map that should be reduced. 2 ways. If you are given a scale, then the scale you are turning to is, where is the given scale? Oh, sorry. This is 50,000. So the question says, a map is drawn to a scale of what? 1 is to 50,000, showing an area in Ghana. You understand? Now they want you to draw this same map with the scale of 1 is to 150,000. I see this. This is 50,000 and this is 150. You understand? Whenever this one, the second, the numerator, the denominator is bigger than this one, then you need to reduce. You need to do what?
Reduce.
Reduce. Exactly.
Yes, sir.
The given is 50,000. The numerator of the given is 50,000. Then the numerator of the one that you want to draw now is 150,000. So which one is bigger? The numerator of this one is bigger. I mean the denominator of this one is bigger. So you're supposed to do what? Reduce. Is that clear?
Yes, sir.
But this 2 scale, which one is bigger scale? This one is bigger. You understand? Do you know why? If you use your calculator and press 1 over 50,000, you know that is the meaning of this. This is a representative scale. Then you use your calculator and press 1 over 150,000. You see that this one is bigger than this one.
Yes, sir.
Is that clear?
Yeah.
Because the denominator is bigger, it makes it to be small. Is that clear? So whenever you're moving from source scale with smaller denominator to the one with bigger denominator, then you're doing what? Reduction. You're doing what?
Reduction.
What if you have 1 is to 150 here and you're trying to get it from 1 is to 150 to 1 is to 50,000? What would it be? Enlargement. You understand?
Yes, sir.
Now, the simpler way of identifying whether you're reducing or enlarging, that's what I want to tell you now. The simpler way.
Okay.
Is that clear? The simpler way is using what we call old scale over new scale. Using what the formula what?
Old scale over new scale.
Old scale all over what?
New scale.
New scale. So what is the old scale?
1 is to 50,000.
So 1 over 50,000, huh?
Yes.
Divided by
1 is to 150,000.
1 over 150,000. So if you are changing the division sign to multiplication sign, what do we have?
We have 1 is to 50,000 times 1 is to 150,000.
1 over 50,000 times 150,000 over what?
1.
What?
1.
1. So we have now what? 150,000 all over what?
50,000.
So if you divide it, what do you think you will get?
You get 3.
3 back.
Yes.
So what will you get?
You get 3.
3. You understand? So what does that mean now? If you want to reduce to this now, what do? You multiply this one by what?
3.
By 3, ba?
Yes.
That's how you get this. So let's say now that you have something that is drawn. Let's draw this in your outline. There's the cleaner. So this is what is drawn for us, which I would like you to replicate. Marianne, how are you going to do this for me now? I've already taught you about
the same size and the same dimension.
River what?
Copy it using
River what?
river more.
Well, which towns are we supposed to locate? We are supposed to locate what?
Yorin and Osha.
Huh?
Yes.
And where? So how can you, if this is what is given, and this one is the scale of what?
One is to 50,000.
One is to what?
50,000.
50,000. So now, how do you replicate it to this scale?
We draw it 3
You
times.
found out that the factor is how many times?
3 times.
3 times. The factor is 3 times, you understand? So you're supposed to reduce this one by what? 3 times. Is it not?
Yes.
So what do we do first? We measure this back.
Yes.
Is it not?
It is.
So if we measure this and this is 10 or 8 or any amount, I will measure this one and this one is also what?
10 or 5 or any amount.
10 or 5 or any amount. Let's say 12. So how do we do to produce a replica of this with the correct scale? What do I do?
Divide both sides by 3.
Good. Divide them by 3. You have what? 3.3, right?
Yes.
So here will be what? 3.3. Is it not?
Yes.
Then I divide the other side by what? 3 again. So here will be what? 4. Thank you. Is it not simple? Anything that you measure from here and here, you just divide by 3. Since 3 is the factor, so you draw. Huh? Now, having drawn, how do you copy this map to here? What do? You divide it, how many, if you want into 3 or 4, huh? Grid, is it not? Grid line. So if this is 10, how many can you divide? How many equal grid can you divide 10 into? Let's say 5. Huh? So you have 1, 2, 3, 4, 5. Is it not? If this is 12, how many can you divide? 4 or 6. Okay. So let's say 6 now. Or even 4. 4 is into 3 times. Huh? So 1, 1, 2. So if you are using that the same way we do this one, this one divided into how many? 1, 2, 3, 4, 5. So we do the same. Equal places,
Yes, sir.
You can do it by just dividing this one by the number of times you want. 1, 2, 3, 4, 5. So how many? 5? 1, 2, 3, 4, 5. Then this one, how many? 1, 2, 3, 4. So 4 divided by 4, you'll be measuring it, which is 1, 1 cm.
Yes.
So once you've drawn the grid, what do? You start transferring, is it not?
Yes.
So to transfer, you just look at it very well.
Yeah.
This man is here, is it not? Then you move down to here, then you call it here.
Yes.
Then he went back here, went here, and went here. Is it not?
Yes, sir.
Do this now. So this Oloro is inside the first one,
Yes, sir.
So now here,
Yes.
this Tosho is in the 1, 2, What else? Finish. So that's how you copy. So we've done two things. What did we do first?
Reduction.
And then copying. Map reduction and what? Copying. That's the two things we did, isn't it?
Yes, sir.
So write it down. Hello, welcome. Today we're going to be looking at rocks in geography. Rocks in geography. Now, what is rock? A rock is any solid substance that forms part of the Earth's crust. This solid substance may be hard, like granite, or may even be soft, like mud. The Earth's crust consists of various types of rocks, and some of these rocks are fine-grained or large-grained. Rocks consist of different minerals. The most common rocks and their minerals are as follows. Number one type of rock is limestone, and the minerals it contains are quartz, feldspar, and micas. Another example of rock is sandstone, and the minerals it contains are quartz, calcite, feldspar. Another example of rock is granite, and the minerals it contains are feldspars, augite. Another example of rock is basalt, and the minerals it contains are calcite, dolomite. Another example of rock is shell, and it contains the following minerals: quartz, micas, and feldspar, just like limestone. Now, let's look at types of rocks. Types of rocks. All rocks are generally classified into three groups according to their origin and mode of formation, as well as physical appearance. These types are: number one, igneous rock; number two, sedimentary rock; and number three, metamorphic rock. So those are the three types of rocks. Now we are going to look at them in details. Igneous rock. Igneous rocks are rocks formed from the cooling and solidification of molten magma from the earth beneath. They are crystalline in nature, and very good examples are basalt and granite. Igneous rocks may be subdivided into two, namely intrusive or plutonic igneous rocks, and number two, extrusive or volcanic igneous rocks. Plutonic or intrusive igneous rock are rocks which solidify deep in the crust, and they are only seen on the Earth's surface after a prolonged erosive action. Examples are granite, diorite, and gabbro. Volcanic or extrusive igneous rock. Volcanic igneous rocks are rocks which have been poured on the Earth's surface, where they are referred to as lavas. These rocks do not contain fossils. An example is basaltic rock, and they can be located in northeastern part of Nigeria. Characteristics of igneous rocks. These rocks are crystalline in nature. They are non-stratified rocks, that is, they do not occur in layers. They are resistant to erosion, and are usually hard and impervious. They do not contain fossils. Sedimentary rocks. Sedimentary rocks are formed from the accumulation of sediments, either by water, ice, or wind. They are laid in layers of strata. These rocks are said to be stratified rocks only when they become harder in nature by compressional forces. All sedimentary rocks are non-crystalline, and they seldom contain fossils. Sedimentary rocks are usually formed through three principal processes, namely mechanically, organically, and chemically. Types of sedimentary rocks. Mechanically formed sedimentary rocks. These are rocks which are formed as a result of action of water, wind, and ice. The following rocks are the results of the action of water, which includes clays, gravel, and aluminium. Those that result from the action of ice are moraine, boulder, and gravel. The only rock produced by wind is loess. Organically formed sedimentary rocks are rocks which are formed from the remains of plants and animals. Some of the notable rocks formed by the remains of animals are chalk and corals. Those that result from plants include peat, coal, and lignite. Chemically formed sedimentary rocks. These are rocks which result from chemical composition. The major rocks formed include borax, potash, gypsum, nitrate, and rock salts. Metamorphic rocks. These are rocks whose structure and appearance have been affected or changed by great heat and pressure. Examples of such rocks whose normal structure and appearance have been affected by great heat and pressure are clay changed to slate limestone, marble, granite, and gneiss. So see all these rocks: shell, coal, sandstone, schist, graphite, and quartzite. Metamorphic rocks change due to heat and pressure. Major characteristics of metamorphic rocks include they often contain fossils. Different colors and texture exist. They mainly occur in layers. The rock may be hard or soft. Difference between sedimentary and metamorphic rocks. Metamorphic rocks are generally more resistant to agents of denudation than most sedimentary rocks. Sedimentary rocks are more permeable, while metamorphic rocks are more impervious. Metamorphic rocks contain non-ferrous minerals, while the sedimentary rocks contain hydrocarbons as minerals. Metamorphic rocks are crystalline, while sedimentary rocks are non-crystalline. Sedimentary rocks have beautiful fossa, while the fossa in metamorphic rocks have been destroyed by heat and pressure. Sedimentary rocks are more jointed than the metamorphic rocks. Sedimentary rocks generally sustain lower relief than metamorphic rocks. Importance of rocks to man. Rocks form the main source of mineral deposits such as gold, diamond, copper, petroleum. Rocks provide the essential raw material for both light and heavy industries, limestone for cement. Rocks could be used for domestic purposes such as grinding stone. Rocks are of economic importance because they aid in construction. Please, if you like this, hit the subscribe button. Please like and share our video. Drop your comments in the comment section. In subsequent classes, we'll learn about land forms. Thank you. Hello, welcome. Today we are going to be looking at map reading in geography. Please, if you like our videos, hit the subscribe button. If you want to cooperate with us in all these videos that we are putting out, please check the description part of this video and contact us. If you have any questions and suggestions on the new videos to make, please drop it on the comment section. Map reading may be defined as the ability to recognize the conventional signs and symbols as used on maps and their descriptions in words of the area mapped with the aid of signs and symbols. Based on the conventional signs and symbols, maps can be classified into the following: atlas maps, topographic maps, and sketch maps. Conventional symbols. We must note that the art of reading a map requires the mastery of a language used by the map makers. The skill will assist the readers to learn and recognize the various signs or symbols used. And until these symbols are logically interpreted by the users of the map, such information will not become meaningful. Therefore, for any student of geography to be able to read any piece of map work perfectly, he or she has to know the basic language of maps. Conventional symbols are the various signs used by the map makers to represent both the natural and cultural features on the maps. The scholar should be able to group such symbols and note the use to which they have been put based on the information mapped. However, there are numerous conventional symbols, but some of these symbols can be grouped thus: line symbols, point symbols, pictorial symbols, literal symbols. Line symbols are used mostly on topographic maps to show features such as rivers, railways, boundaries, roads, telegraph, telephone lines, etc. The student must show the type of line used in each case when reading his map, as well as drawing by using proper colors. Point symbols. These symbols are used to show features such as trigonometrically station, benchmark, farmhouses, as well as settlements. Point symbol can equally be used in combination with literal or alphabetical symbols to show some vital facilities such as schools, courts, post office. Pictorial symbols are the first set of symbols used by geographers to represent relief. They are straightforward techniques to represent features in form of drawing, that is, the pictures of the features in the place where they are found. This method enables the map readers or users to know the various features represented on the map without necessarily referring to the map legend. Literal symbols. For these symbols, letters are abbreviated to show the location of features, particularly those facilities that are important. Example, CH for church, MKT for market, RH for rest house, SCHL for school. So in subsequent classes, we'll go through map scale and other things. Please hit the subscribe button immediately so that you'll be getting our videos whenever they drop. Drop a comment in the comment section and ask me any question that you want to. Check us out on the description section. Support us in any way that you can. Thank you. God bless. Hello, welcome. Today we are going to be looking at bearing in geography. The two principal ways of showing directions are through the use of compass points and angular bearing. So whenever you want to show directions in geography, there are two principal ways. One is by using a compass point, and two is by using angular bearing. Now let's look at compass points. This entails the use of 4 cardinal points, north, south, east, and west, to show the direction of places. Students are advised to stick always to the use of the 8 cardinal points for examination purposes. For example, what is the direction of town X from Y? So these are ways described in subsequent videos showing the diagrams. Note that you view your direction from point Y, hence your cardinal point should be centered on point Y actually. Therefore, the direction of X from Y is northeast. Now let's look at the second point, angular bearing. I'm going to demonstrate this in subsequent class, so don't be afraid. Angular bearing refers to the difference in angles between two places, the true north and the true north. So that very difference in angle between two places and the true north is known as angular bearing. The bearing of the post office, for example, refers to east direction with reference to the person making the observation. In this situation, a line drawn to connect the angle formed between the line and the true north is therefore called the bearing. Bearing is measured in degrees and in a clockwise manner with a protractor. Very important, note that. Method: place the protractor correctly. The center of the protractor should be at the center of the cross. Then read the bearing in a clockwise direction. For example, what is the angular bearing of the principal's office from the school gate, the assumed position of the school gate, and the principal office? So take note of all these. Subsequent classes, we are going into physical geography and other forms of geography. Please, if you like this, hit the subscribe button immediately. Share our videos, or drop any comment and concerns in the comment section. Check out the description part of this video to contact us and support us in any way you can. Thank you, and may God always bless you as you continue to help us to help you. Thank you. Yes, listen up, listen up, listen up. No noise, no noise. I'm recording. Yes, please don't draw. Listen first. Let me explain.
Okay.
Drainage pattern. What is drainage pattern? Drainage pattern is simply a path showing how water moves, is it not?
Yes.
A path showing how water
Moves.
and that water could be in form of river, sea, or anything, isn't it?
Yes, sir.
So this is the shape taken by a river and it's what? Tributaries. You do know what they call tributaries?
Yes, sir.
If the main river is moving like this, and there is a small part where small river will move, that is the tributary, is it not? The main river and what? Tributary, the branches. Tributary simply means what? Branches of the river. So drainage pattern is simply the shape taken by a river and its what? Tributary. It is an important landform shown on what? Topographical maps. Whenever you're looking at topographical maps, you will see the rivers. You understand?
Yes,
you see
sir.
the drainage what? Pattern. And this drainage could be surface drainage or what? Underground. When rain falls, you understand? And water is moving on the surface, is known as what? Surface drainage. But rain can also move on the ground, isn't it? Underground. Now, types of drainage pattern. What are the types of drainage pattern we have? Can you look at this?
Yes, sir.
These are the forms of tributaries, the main river and its tributary that you can have. Can you see this one?
Yes.
This is the main river. You see the tributaries.
Yes.
It's in form of as if it's a tree. Is it not?
Yes.
So whenever you have this pattern, you call it what? Dendritic. You call it what? Dendritic. And this dendritic pattern of drainage is found in areas where there is relatively what? Homogeneous rock. You understand? Any area that you have all the rocks there are soft, or all the rocks there are what? Hard. You find what we call dendritic pattern. But you look at this place, you see what we call, the second one is what we call sterilized. You understand? In sterilized pattern is where you find it mostly, is where you have alternative soft rock and what? Hard rock. You have them together. Is that clear?
Yes.
You have this shape. Can you see the difference between these two shapes?
Yes.
This one, the tributaries are meeting it at an angle of what? 90
degrees.
But this one is meeting it at an oblique angle. Can you see that?
Yes.
Take note, see. The joining is done at oblique angle for dendritic, whereas for sterilized it is done at what?
Right angle.
This one mostly looks like a straight line, isn't it?
Yes.
With right angle triangle, but this one is oblique angle.
Yes.
But there is this third one we call what? Radial. We call it what? Radial. You find radial whenever you have a cone or a hill and water is falling down. So they tend to be what? Separate from the hilltop, is it not? Just like what we have here. This, let's say this is the hilltop. You understand? Or maybe you're having water coming down from it. It will separate as the hill is. You know, hill is something like this. Is it not? So if you put water here, how will the water fall? Is it not? You move like this. So this is what? Radial. Then we have the last one known as what? Annular. How does annular do? You have a something here blocking the motion of the water, and the water is moving. Once it reaches there, it will do what? Divert. That is annular. The water is moving like this. It comes here and sees something like a hill or something. It will do what? Divert. This is annular. This is radial. This is sterilized, and this is what? Dendritic. Is that clear?
Yes, sir.
So those are the patterns of drainage patterns that you have. God bless you. Landforms. Today we are going to be looking at landforms. There are three major types of landforms, namely mountains, plateaus, and plains. The focus that produce landforms, the forces that produce these landforms are both internal and external forces. When you go to some places, you see mountains. If you go to some places, you see plain land, and in some places you see plateaus. So these are the landforms. In Gogolada here that we are in Abuja is majorly plain land. If you go to Plateau State, you see plateaus. If you go to other places in the east and west and north, the Olumo, you see the mountains. Now, there are forces that make a landform to either be plain land, plateau, or mountain. So let's look at these forces that cause this. We have the internal forces. These are forces which operate within the crust. The earth movement is of two types. We have the vertical and lateral movement. Now, the vertical movement is the up and down movement which causes the crystal rocks to fall. Features produced include block mountains, plateaus, and basins. So the vertical movement, which is pushed by the vertical force of earth movement, causes things like block mountains, plateaus, and basins. Now let's look at lateral movement caused by the lateral force. This is the sidewards movement which caused the crystal rock to fold. Features produced are fold mountain and rift valley. Volcanic eruption could be affected in two ways, namely internal, external eruption. External eruption is that which the lava gets to the surface of the earth, producing features like lava plains, plateaus, volcanic cones, etc. Internal eruption refers to the lava which solidifies in the crust, producing features like dike, site, sills batholiths, laccoliths, etc. Now let's talk about external forces. These are forces that operate on the Earth's surface and they are caused by the agents of denudation and depositions. Agents of denudation and modifying agents. Agents of denudation. The following are the major agents of denudation responsible for the formation of landforms. Number 1, weathering. This is responsible for the breaking up of rocks by alternate heating and cooling, chemical action, and the action of living organisms. Erosion. The breaking up of rocks by the action of rock particle being moved over by the Earth's surface by water, wind, and ice. Agents of deposition. So you see the two agents of denudation, weathering and erosion. But the agents of deposition are the following are the forces responsible for the development of depositional features on the Earth's surface. By water. Number 1, by water. The resultant landform by the action of water movement are floodplains, levees, alluvial farms, delta, alluvial plains, etc. Number 2, by ice. The action of ice, thawing or movement on the Earth's surface produces features. Transportation. The movement of rock particles over the surface by water, ice, and wind. Subsequent classes, we are going to be looking at types of mountain, and we're going to be going from there. Thank you. God bless you. Please subscribe to our channel, like and share our videos. Support us in any way that you can. Thank you. God bless you. The Earth structure. Welcome. Today we're going to be looking at the Earth structure in geography. The Earth structure is divided into groups, namely the outer zone or structure and the internal zone or structure. The outer structure of the Earth is made up of the following layers. Number 1, the atmosphere. Number 2, the hydrosphere. And number 3, the biosphere. So those are the 3 layers making up the outer structure of the Earth: the atmosphere, the hydrosphere, and the biosphere. The atmosphere. The atmosphere is composed of a mixture of gases which forms an envelope around the Earth. The atmosphere contains 78% nitrogen, 21% oxygen, 0.03% carbon dioxide, and 0.97% inert gases. The atmosphere is of great importance to both man and other living organisms. Why? Because it provides gases which are essential for respiration. It provides nitrogen for plants. It contains the ozone layer, which acts as protective cover for living organisms against the burning effect of ultraviolet rays of the sun. It acts as the habitat of some living organisms. Hydrosphere. The hydrosphere refers to the water masses which include rivers, oceans, and seas. It is the liquid portion of the earth, and it occupies about 70% of the total earth crust. The hydrosphere holds water in both solid and gaseous forms. The importance of hydrosphere to man and other organisms are as follows. It provides water for both domestic and industrial uses. It creates employment for the people dwelling in the riverine areas. It can also be used to generate electricity. It is used for irrigation scheme. It encourages tourism. So those are the importance of hydrosphere. Biosphere. Biosphere is the biological active part of the earth. It consists of plants, animals, and microorganisms. These concepts can be subdivided into biocycles, namely freshwater biocycles, saltwater biocycles, and terrestrial biocycles. Both the freshwater and saltwater are under the aquatic biocycles, whereas the terrestrial biocycle is on the land. It is possible to recognize zones where certain life forms are adapted to environment. Therefore, terrestrial biocycle can be divided into the following biocycles. We have the forest biocycles, the grassland biocycles, and the desert biocycles. Biosphere 2. The forest biocycles is made up mainly of rain and deciduous forest, whilst the grassland biocycles is made up of Guinea, Sudan, and Sahel savanna. The desert biocycles is a bare earth surface. The importance of the various biocycles in the biosphere to man. They produce plants which provide food for man. They provide source of energy for man. They aid the balancing and purification of the atmospheric gases. They provide raw materials such as timber, hides and skin, cotton, etc. They create employment for man and in form of agriculture. Now we look at the internal structure of the earth. The internal structure of the earth is made up of 3 concentric layers. We have the lithosphere, have the mantle or mesosphere, then we have the core or bariosphere. The lithosphere. The lithosphere comprises 2 parts, namely the cl and sigma. The cl has a relative density of 2.7 and consists of granite rock, while sigma is denser in weight with a relative density of 3.0 and comprises basaltic rocks. Cl is richer in mineral constituents known as silica and alumina, while sigma is rich in silica and magnesium. The mesosphere or mantle. The mesosphere lies beneath the lithosphere. It is very thick layer rich in a mineral constituent called olivine. The bariosphere. This is the innermost layer, also known as core, which was generally believed to be in liquid state because of the high pressure and temperature in the interior. Bariosphere is made up of mineral constituents known as nickel. So the internal structure of the earth, you're talking about inside the earth crust. So we have the lithosphere, which is closer to us, the silicon, the sand. Now under it we have the mantle or mesosphere. Then we have inside the core or the bariosphere, composing of nickel mostly. The mesosphere or the mantle is consisting of olivine, whereas the lithosphere, which is made up of Cl and sigma, Cl on the up and sigma down, is made up of silica alumina, and sigma made up of silica and magnesium. Please take note of all this. So in subsequent classes we'll be looking at the rocks. Thank you. Please subscribe to our YouTube channel, share our videos, support us by donating to us in any way you can. Check the description part so that you see our account number and how to donate to us. Thank you and God bless.